So hello everyone and welcome to today's Bite of Science webinar presented by the Teacher Enrichment Program of the Center for Excellence in Education. My name is Shannon Tyler and I am the Teacher Enrichment Program Manager. I will be hosting today's webinar titled Exploring the Power of Mechanical Engineering. We are very excited to hear from today's speakers, so let's get started. To begin, I'm going to share some brief background information on our organization. The Center for Excellence in Education was founded in 1983 by Joanne DeGennaro and Admiral Rickover, father of the nuclear navy and civilian uses of nuclear power. Its mission is to nurture high school and university scholars to careers of excellence and leadership in STEM. We have cost-free programs for teachers and students, including the Research Science Institute, RSI, USA Bio-Olympiad, USABO, the Teacher Enrichment Program, TEP, which is hosting this webinar today, and STEM Lyceums. I'm going to talk a little bit more about these programs now. So first, we have the Research Science Institute, or RSI, which is a highly competitive 6-week summer science and engineering program open to rising high school seniors, so juniors are eligible to apply. RSI is the first cost-free summer science and engineering program that combines on-campus coursework in scientific theory with off-campus work in science and technology research. Next, we have the USA Bio-Olympiad, or USABO, which is the premier biology competition for high school students in the United States. It provides the motivation, curricular resources, and skills training to take them beyond their classroom experience to the level of international competitiveness. A fun fact about the USABO is that since CEE began administering the test in 2003, every member of the USA Biology or Bio-Olympiad team has medaled at the International Biology Olympiad. Next, we have the Teacher Enrichment Program, or TEP, which provides opportunities for middle and high school teachers to connect with leading experts from industry and academia, explore cutting-edge research and development, and make meaningful professional links with direct benefits for educators and their students. Finally, we have our newest initiative here at CE, STEM Lyceums, which is a virtual club for high school students to meet once a month to learn about STEM career pathways from leading field experts. Industry professionals share cutting-edge research and offer unique learning experiences like scholarships and internship opportunities for high achievers. To learn more about our programs and opportunities, please visit our website at www.ce.org. Before I introduce our speaker, I would like to encourage you to take notes while you listen and to ask questions throughout. Please submit your questions through the Q&A function or in the chat, and they will be addressed by our speaker at the end of the presentation. Now, I'm very happy to introduce today's speaker, Dr. Eleanora Tubaldi. Dr. Tubaldi is an assistant professor in the Department of Mechanical Engineering at the University of Maryland, College Park. She received her PhD degree at McGill University in mechanical engineering. Her research focuses on the study of stimuli-responsive metamaterials, bio-inspired soft robots with sensing capabilities, and soft tissue mechanics. Recently, she has been awarded the 2024 ASME Henry Hess Early Career Publication Award, 2023 NSF Career Award, and the 2020 Haythornthwaite Young Investigator Award from the ASME Applied Mechanics Division. Thank you to Dr. Tubaldi for joining us today. We welcome you and we look forward to hearing your presentation.
Great. Thank you so much for the very kind introduction. It's a real pleasure and an honor for me to be here today and have the opportunity to share with you a little bit about the research in our lab. So we work on a variety of topics that revolves around soft intelligent materials for actuations and sensing with soft robotics applications. So most of our inspiration comes from nature. So I would like to start by showing you how, for instance, nature achieves very fast motion. So for instance, you might have seen a very hungry Venus flytrap that is catching its prey with this closing, like locking mechanism very fast. Sometimes it's going to miss its prey, sometimes it's going to get it. But this is a mechanism that we really want to explore and try to leverage also in our designs. And this is based on a mechanical principle that's called snap-through instability. So we'll talk more about it in a second. And then if we scale down, we're going to look, for instance, at the vibrant Genelidicus, where we see that this can turn very quickly, like in a fraction of a second, by having this buckling instability of its tail. So nature leverages these fast reconfigurations for different purposes. And as engineers, we are interested in learning from it and including these type of principles in our designs. So now how can we achieve fast motions in mechanical systems? So if we want to use the Vibranch Analyticus approach, like in snap-through instability, we can, for instance, see here a case where we push like a 2D plate, and this is going to all change shape very quickly and is going to shrink it in all directions. Or here we're going to see another type of arrangement of materials. Once we compress it very fast, it's going to show one deformation. If we compress it slowly, it's going to change its deformation. So speed is going to play a role. We can also include sequencing. So we want to try to achieve sequential motions with very simple inputs. So here you see, for instance, an origami robots, where by actuating, so inflating and deflating it with different sequence orientation, we're going to get to different targets shape. And at the bottom here, we see by cutting a material with pores inside, this is going to be able to change its angle on how it's attached to the base. So in this way, friction is going to change, so locomotion can be achieved and programmed in the material. And here you see the example on the locomotion of the soft robot. And then we also want to achieve gentle grasping. So achieving something very fast but gentle at the same time is a challenge, is an important challenge that we have in our designs. So we can use the snap-through instability, like we've seen in the previous Venus flytrap case, and also buckling for this curly type of grasping task, where filaments are being actuated upon deflation, and they're all going to curl because they are not symmetric, so they're going to bend one way or the other, and this is going to enable to achieve different touch points and grasp complex objects. So we see that this gives us, a lot of possibilities in the design of shape-changing material, embedding sequencing, and gentle grasping. So we would like to advance the research and the field in all these different areas. So we ask ourselves, for instance, how can we achieve this programmable shape reconfiguration by leveraging a principle in geometric frustration? We're going to see in a second what I mean by that. We would like to achieve sequencing capabilities. So when we inflate a material, like it looks like a balloon, but it's an intelligent balloon. It's something that once it's inflated, is going to be able to trigger different touch points and interact with different objects. And then we want to achieve also gentle grasping. And while we're grasping an object, we also would like to sense, to learn something about the object. So we're going to talk about all these 3 different projects to give you a flavor a bit of what's going on in our lab. So in the first topic, we have 3 students working on it, PhD students Michael Bontron, Terence Pierce, and Daria Holman as undergraduate students. So now, what is the snapping I was talking about that the Venus flytrap uses, right? So it's like if it's storing energy, like we can do when we eat, for instance, an apple, and then we want to run. So in the same way, it's like when we compress a spring and then we release it all of a sudden. So there is a lot of energy that's stored there. And this is going to then give us a fast reconfiguration. And it's the same thing when we have a ball at the top of a hill. We give it a push, that is going to roll down. So it's going to change its potential energy from when it's high up on the hill and when it's going to be down the hill. So we can use the same principle in designing structures. So if we start with a flat plate, it doesn't have any potential energy. When we start compressing it, now we see that we have 2 minimum where the structure wants to be. So either up in this case or down in this other case. So how is it transitioning from the top to the bottom configuration? Is gonna go through an unstable state. So you see here that is this shape that is like a sine shape, is going up and then down. So if we look at the potential energy here, we're higher up here, and then we go down to the other minimum. So just this basic principle, we leverage it when we combine multiple of those plates. So this is what we call metamaterials. So metamaterials are materials whose property emerge from structure rather than composition, meaning that depends on how I combine these different plates, I'm going to get different shapes. And I want to transition from one shape to another shape with simple inputs. Why I want to do that? Because this can be used for sending signals. So in the same way we have, in our computers, for instance, we have diodes, we're going to send signals from one way and not from the other way. We're going to do the same thing with a mechanical system, because this allows us to store a lot of information and then to release it upon demand. And also we can think of applications like energy absorption. So we like to store energy and have it released when, for instance, we need to hit for a bumper. And this is going to absorb all our energy, and the car then, even if it's going to hit a wall, is going to feel safe behind that. So these are all mechanical principles that we want to be able to program into our material. So now for the fast shape reconfiguration, so we said, okay, we're going to have a high energy state that, let's say, it's in a vertical position, like if we think about the domino, and then it's going to be a lower energy state when the domino is going down. So what is happening from the potential energy perspective? So when we have our domino hole standing up, this is going to have a higher minimum. Then it needs to overcome an energy barrier, so increase the energy potential, and then fall down into the lower energy state. So when this is happening, what is going to happen if we put one domino next to the other one? So there is going to be a chain reaction here, right? So we push the first element, all the other ones are going to fall down, right, in a sequence. So if we look at the energy profile of each single element, once the first one is going to fall down, the second one is going to start falling down, and so on and so forth. So we want to embed this chain reaction, so this shape-shifting mechanism, into our system. And people have studied that, for instance, with different plates that you can combine in this 1D arrangement, and you have magnets here. So when you push on one magnet, then all of them are going to trigger the response. Same with this rotating square, or also with this spring loading mechanism that by touching the structure, then it's going to all change shape. So why do we like this very simple actuation? Because these things can be deployed, for instance, in exploratory missions in new planets or in underwater systems. So what we want to do here is combine these different building blocks, so these different dominoes blocked in different arrangements. So they can all be asymmetric, like the one we showed, so domino up, domino down, or they can all be symmetric, like the plates I was showing in the initial snap through. So now what is the difference? In the first case, we are going from a configuration up to a configuration down. And in the other case, we have this gradient, right? So the energy barrier, so the amount of energy that we need to put to jump from one state to another, is going to decrease. And we have different examples for all of them. Now, what are the drawbacks? In the first case, like, we need to have this asymmetry in the energy wells. In the second case, we need to have a finite size, because overall we keep decreasing and decreasing our energy barrier, and eventually we're not going to have these two stable states anymore. So then we introduce this concept of, can we use the arrangement and use in particular geometric frustration to transition from one stable state to the other. So we start with our buckle beam, so with our beam that we compress, and then we arrange it, so we tessellate it in triangles. And triangles are very peculiar. Why? Because we can have one beam that is up, one beam that is down, and the third beam doesn't know what to do, right? Because it's feeling these different constraints. And the same is going to happen in the reconfigured state, where we still have triangles. And in jumping from one to another, we are going to release energy. So what we want to do, we want to have a shape-shifting material where we give it an input on the first elements, and then this is all going to transition like the domino effect that we showed before. So we start with our beam, and we see how by rotating on one end, it's going to jump from one stable state to the other. And we see that this is all symmetric. Now, what happens if we put multiple of these beams, one after the other one? Well, we see that by actuating one, the second one is going to follow. And we can propagate this through chains. So we can become really creative. So the beauty of metamaterials is that everything depends on the arrangement, right? So we can create triangles, we can create square, rhombus, or hexagon materials. And then when we go at the metamaterial scale, so we can build these large networks, we can have all different arrangements by using the same building block. So in initial state, this is unbuckled, so it's a straight square and it's a straight triangle. And then when we put them in the supports, we see the buckled state. So this is going to be up, down, up, down. And then when we do the same for the triangle, that's where we see the frustration coming up, because this is up, this is down, and the third element doesn't really know what to do. So this is like the spins in electronics material. So we want to be able to use more energy that is stored in the system to release it for propagation. So here are different configurations we can play with. So we have an asymmetric configuration, and then we have a geometric symmetric configurations. So we recognize that by the different axes of symmetry. And then we can become creative by increasing the rise. So we push the size of it. So we see how the height B is increasing, and we see what are the different stable states. So initially, the structure is a 0 state, then it's going to get into the asymmetric state, and then finally it's going to get into the symmetric state. So we can control in which state we are going to be. So we want to go from the high energy well, so from the high energy configuration to the low one. So we can be very creative in the arrangements, and so we can think about different structures and different topologies. So we study the hexagons, and what we see is that the way we arrange them, we're going to have a symmetric and anti-symmetric arrangements. So depending on how we actuate them, so we push or we pull them, we see how the structure is going to change its shape, either clockwise or counterclockwise. So we end up in a lower energy state configuration, but we gather information about the inputs as well. So here we see an arrangement with 4 unit cells. So we pull on the first one and we push on the second one. And then we can expand that to 20 unit cell. And you see how the wave is propagating. So initially everything is red, and then we see the wave profile turning blue. That is sequentially actuating. So this is happening just because we arrange these elements in this specific topology. So we are only actuating, pushing or pulling the first elements on the left. So this is interesting because it's gonna give us a way to guide a wave through the structure. Let's say we wanna protect a payload. We're gonna put this material all around this payload. So the energy is gonna be dissipated around it, and it's gonna keep our payload safe. So in this way, we learned how by arranging very simple units, we can actually gather very intelligent behavior and program the transition front. Another interesting aspect of the structures is that they store memory, because even if we don't see the transition going on, if we set our material in one state, and there is an excitation coming over that could be a displacement or a temperature change, then we're going to look at it again and we can get information that something happened to the material. So those are all intelligent behaviors that we want to be able to embed into our structures. So with this, we conclude the fast reconfiguration part of the talk. Now we're going to talk about advanced sequencing into soft porous materials. So in a way that we have a soft robot that can sequentially perform different actions. So here I would like to thank the PhD student Kieran Barbanik and Michael Bontran and the master student Anthony Jones from our lab. So now let's talk a bit about buckling-based metamaterials. So here what you see at the top left is a piece of rubber, literally, with pores in it. So what is interesting about it? That once we compress it from the top to the bottom, we see that all the pores are going to collapse, right? And what is the end result is that this material is going to shrink in all directions, right? So it has a negative Poisson ratio, so it's called also auxetic material, because typically when you compress a material in one direction, it's going to expand in the other directions. But here you can see that everything is going to be shrinking down. So this can be used also to trigger an actuation. Let's say there is a deflation that is being applied to those cavities so that the system can actually move. So it's a soft robot that can locomote. Or we can program some elements, for instance, to come out and some elements to compress in. And now we see in this cube, you see a smiling face coming out just by compressing the material. So this gives us the powerful aspect of mechanical metamaterials based on this buckling instability, where we can program response. So here you see all the actuations are on deflation or on compression. Now we ask ourselves, can we inflate a material? Can we really, if we are inflating a balloon? So this is the traditional rubber that I show you. So when you cut a piece out of it, like get a slice, you will see that's all full inside. So the pores are gonna then reconfigure, so change their shape, and they become like ellipses, and there will be one ellipse horizontal and one vertical, and the opposite in the lower row. So now what we want to create is a cavity inside this material. So in this way, we can actuate it with negative pressure, like in the other examples, but also in positive pressure. So why do we want to inflate this balloon? Because we can get different potential responses, like diamond, alternating ellipses, or these three lobes, like a flower mode shape. So to achieve that, we started thinking about the structure, and we manufacture it in a way that we can just inflate it with a single input, and then they're going to share this pressure inside the cavity. So then if we look at it on our piece of it, we can see that it's like a 2x2 arrangement. And then we have a single cylinder with the plates at the top and the bottom. So we started looking at what would be the global shape that we would expect. So we see that we can have diamonds. So we introduce these diamond reconfigurations. And then we look at how we can predict the behavior. So we use equations to identify what is the critical pressure for which the shape change is going to happen into our material. So we use also finite elements, so numerical simulations, to predict the response. So all our research is based on analytical, numerical, and experimental components, because we want to be able to predict how the structure is going to behave when different pressures will be applied to it. And in this way, we can find the critical pressure at which the structure is going to change its shape. So we also do experimental validation. So just by changing the height of this material, we get different responses. Like here, we got a diamond mold shape. Now, if we make this shorter, we're going to get an alternating ellipses. And if we make it even shorter, we're going to get a 3 lobes, so a flower shape. So we say, okay, we like all this because with different heights, we get different pressures and we get different deformations of our special balloon here. So now we compared what we get experimentally and what we see numerically. So this colored version of the metamaterial at the center is what we predict numerically. And on the right-hand side, we are plotting how the volume is changing inside the cavity of this balloon versus the pressure. And we compare analytical, numerical, and experimental results. So we see all the 3 different regimes. So this is the diamond that emerges with a critical pressure of 0.5. This is non-dimensionalized value. And then alternating ellipses for higher pressure. And then finally, the 3 lobes, so for even higher pressure. So we see that we can control the deformation here, and we got very good agreement within the numerical and experimental results. So now we want to use it for soft robotics applications. So why we think this is interesting? Because we have the collapsing of the pores that represent different touch points. So these different touch points are a different way of having an actuation mechanism. So something we can do is to make a critical pressure on one side of the structure and a different one on the other one. So then when we inflate our balloon for a pressure that is in between these two critical pressure, we will have only one column that is going to deform. And then if we keep increasing it, then we're going to have both columns that will respond with different mode shapes. So what we decided then to do is to grab test tubes. So here we are inflating our material, and we inflate it between the two critical pressures in a way that we're only going to grasp one row. So just by setting the pressure between P1 and P2, we say, okay, we just want to grab the red test tubes column. And that is exactly what happens because the column on the left is now being deformed. Now, if we want to grasp both columns, now we're going to increase the pressure above the highest critical pressure. So with a single input, so remember it's just a balloon, so we just inflate it and deflate it, we can selectively grasp different portions of the structures we are interacting with. So we then decided to look at a smaller sample, so where we have only two pores, and we decided then to use it to mix coffee and cream. So here we have two different pores where there are two different tubes that go through it. On the left one, there is coffee. On the right one, there is cream. And depending on how open or how close they are, we can get different percentages of coffee and cream. So we like to call this the barista material because this can give us different percentage of coffee. Each of us have our own preferences, just by controlling the opening and closing of these pores. So we actuate only these cavities, and then the material is going to do the rest to do the mixture that we like. So in this way, we show that we have different shading of, from black coffee to coffee with cream, and we can control the ratio between the two. So in a way that we can control the fluidic mixture. Of course, we can expand this to different fluidic components. Now here we just demonstrated with coffee and cream, but you can think of having a lot of different fluids that you want to regulate. So this material gives you the opportunity not only to grasp objects, but also to do fluidic control in a variety of applications. Okay, great. So with this second part of the talk, so we went over the sequencing capabilities of soft intelligent materials for soft robotics applications. And now the last one I want to talk about is about gentle grasping, but grasping with a sense of touch. So being able to grasp objects and getting information about it. So for this project, I want to thank my PhD students, Kiran Barbanik, master student Zachary Coogan, undergraduate students Priya Nayak, and our collaborator from Aarhus University, Matteo Pezzullon. So how can we achieve gripping, and in particular, soft gripping? So there are different strategies. So the first one is to use a granular material gripper. So here you see this granular material that is inside the soft balloon that is made of all granular that is being deflated. So once it's being deflated, this is compacting all around the material, so it's going to allow that to grasp it and to move it around. So it becomes very rigid once it's being deflated because all the granular material is going to become super compact and stiff. Another strategy is to use this gentle grasping. So here you see these thin filaments where there is a cavity inside and the beam is asymmetric. So when we deflate it, that is going to bend and can grasp a jellyfish that is an extremely delicate and fragile animal. And then another approach is to use kirigami. So in kirigami, we make cuts on thin plates, and then we pull them to see how the deformation can go out of plane. So here we see there is a cut at the center of this material, and once we pull it, the two sides are gonna bend. So this is gonna be then able to grasp different objects. And then another strategy that we can use is the snap through. Again, like we said at the beginning with the Venus flytrap. And in this case, what happens is that there is a shell at the top, so a dome that is being deformed up and down. So these appendices then can wrap a strawberry in a very delicate and gentle way. So these are all different strategies that can be used for grasping objects. So something we wanted to achieve is to get complex object grasping, and in a way that we can tune the force output, we can protect the objects, because oftentimes we want to be able to encapsulate the object and protect it from outside. And then we want to be able to sense something about the object. So maybe what about size, shapes, material. So again, we turn our attention towards nature. So we thought, okay, what can we do? So one of inspiration was a Pac-Man that can grasp objects. And nature, what it does it is with this tunicate that is a deep sea creature that is made of a siphon that is going to open and close is this gigantic mouth to feed himself. So inspired by this mechanism, so we developed what we call our Pac-Man gripper. That is this dome, basically, so where we have a cavity inside and a very soft deformable layer at the base. So once we deflate it, we can get to grasp, for instance, here we have orbits that are wet, so they're very tricky to grasp with our hands. So here we showcase that we can turn it in a way that is super safe and is very reliable as a mechanism and get them to move around. So we studied how the deformation happens. So everything will depend on how thick this shell at the top is, and then how tall overall the shell is. I'm going to skip over the math, but if you have questions, feel free to ask. Well, why we do this? Because we want to be able to program what is the critical pressure at which we are going to get the deformation. So we always want to be able to control our structure and its response. So we do simulations to see how the deformation happens in a way that we get our Pac-Man shape, because we want to be able to encapsulate objects. So we need to wrap our dome around those objects. And there are some plots where we control what is the critical pressure versus the non-dimensionalized thickness of the shell, and also with respect to the cap angle. So there is some digging and design space definition so that we know, depending on which application we want to target, what type of behavior we want to expect. And this is our gripper geometry. So it's a very simple dome with this thin membrane at the base. So what are the geometrical features that matter? So this is going to be the ratio between the thickness of the dome and the membrane, and also the film thickness divided by the radius. So we design these domes to go through all different pressure levels, and we see which ranges we get. And then we identify different regimes. So this is to demonstrate you that we cannot take any dome and any membrane at the base to get the Pac-Man shape that we want. There needs to be a specific ratio between them. So we can be in different regimes. So if the membrane is too thick, then the dome is not going to have enough force to go in the Pac-Man shape, and it's going to buckle with this dimple. Then if the ratio between the thickness of the membrane and the thickness of the shell is in a regime where they can compete, then we get the Pac-Man. That is what we get as constructive buckling. And then if the membrane is too thin and the dome is too thick, once we deflate it, the membrane is going to just be absorbed. So now we're going to see all this in videos where we compare the experiments at the top and the deformation that we see on numerical simulations at the bottom. So here we are deflating this Pac-Man, and and we see how we get the dimple. So it's gonna jump, but this is not useful for us because we don't get the grasping. So then we try to increase a bit the thickness of the membrane. And that's when we see that both the dome and the membrane at the base, they're gonna cooperatively buckle. And we see how the shape is gonna change, and this is gonna be functional for our grasping purposes. And we'll always compare how much volume we need to change versus the pressure that we measure. And then the last case is not very interesting because we just see the membrane going up and the dome being too stiff. So the dome is now moving because it's too rigid, the thickness was too high. So this is to demonstrate that there is a range for the design space where we can get our interesting response. So now what about sensing? So sensing comes when our structure, so our dome, is going to impact an object. So here we see that we have three different objects. So we have three different cylinders, one very small, one intermediate, and one big. So even if we don't deflate it, once we touch the object, the cavity is going to change its shape. Bigger the object is, bigger is going to be the change in pressure that we're going to measure. So indirectly, just by looking at the pressure volume curve, we are getting information about the objects. So even if we don't have cameras, even if we don't see that, we can see that the fuchsia curve, is interacting with a bigger object than with respect to the violet and with respect to the light blue. And we can detect important points, like when we contact the object, when we grasp the object, and when we release the object, just by looking at this one single pressure curve. So we're not adding any sensing. We're not adding cameras. We're not adding additional electronics here. So now we want to demonstrate that we can grasp lots of objects, and we can get also a sense of when we have the contact, the grasping, and the release. So these are very jelly type of materials. So this is a piece of tofu, for instance, and we see where the contact happens because we compare it with respect to the curves when there is no object. We see, for instance, with a raspberry. So the beauty of this is that the pressure is going to be regulated around the object, and the deformable component, so the membrane, is the one that is in contact with the object. So we can also have stiffer objects like screwdriver that are way bigger, for instance, than the dome itself, than our Pac-Man, but we can successfully grasp it. And then here we became really creative, and we said, okay, let's try an electronic chip. Why not trying Lego person? Why not trying strawberries, broccoli? So all of this, we can successfully grasp it and get a sense of what shape we are handling. So as we are thinking about this soft repair with sensing capability, we think it also to deploy it for soft robotics in the biomedical field. So this means that we need to go through very narrow passages. We might not have, we don't want to damage tissue around us, right? So this is the ideal design because it doesn't have any stiff component on the dome and there is no additional sensors. So here we show how we can move an object from one side to another, and we can sneak through a very narrow passage. And we can define where the contact, grasping, and where the release are. So another application we thought is about, cleaning the oceans. So being able to grasp plastic sediments. So why it's tricky to grasp these plastic sediments? Because they change shape while we are grasping them. And also they can be really, really heavy because they can carry water. So the good thing about this dome is that it's going to adjust its shape around the plastic. And in this way, we can successfully grasp it. Then the last test we wanted to do was with our testudo, right? With our mascot from UMD. We tried to grasp it and we couldn't. To say, oh, no way, like testudo cannot betray us. So let's think about it, say what's going on. Testudo has a very complex shape, different, like the head, the shell, so different appendices. So then we said, okay, let's try to enhance our versatility here. So traditionally, our Pac-Man can only deform in this mode shape, right? It's going to wrap around the object. So then we said, can we change the gripping force and can we change the deformation? So what if we want to get more complex shapes? And to do that, we started thinking of adding elastic connections at the base. So this is the way we make our Pac-Man. So we make the shell, we make this lower, stiffer membrane, and then we combine them. So now we start thinking of using also high stiffness components into our membrane so that we control these pinpoints. And we keep the same manufacturing principle. So in this way, we can control how many lobes, material, width, and height we have. So this is the tests that we did for this case where we have three pinpoints. So we have this stiffening component into our membrane. We see we can predict its behavior. And then we went back to our studio. So we said, okay, let's see now if we can get it to studio. So here you see the stiffening components into the membrane. We approach the studio and we can successfully grasp it. So this tells us that we can, expand a lot our design space and grasp very complex objects with different shapes with a simple edit into the design if needed. Yeah. So with this, I would like to thank you for your attention. Thank you all the group, our sponsors, and I'll be happy to take any questions.
Thank you so much for that wonderful presentation. I thought it was very interesting.
Thank you.
So yes, we will now open the floor to questions. If you have any, please feel free to drop them in the chat or in the Q&A. I'll get us started while people formulate theirs. You talked about it a little bit, but can you talk a little bit more into some of the real world applications of your work?
Sure. Yeah, so the great thing about developing these soft robots without electronics into it is that we can use them and deploy them, for instance, into the human body if we are doing, for instance, an MRI. Because there are lots of scenarios where we want to be able to monitor certain conditions or maybe doing some operations, surgical operations in these states where we might need to be in an MR. And that is very tricky to do with traditional components. So we want to go in the direction of surgical robots that can be embedded into more complex designs by keeping this intelligent behavior from soft and safe components that we can leverage. Another direction we are pursuing is to have assistive robotics. So these soft grippers can help as an assistive device for people who might need help in grasping objects, as they're very safe to interact with humans. And this can also give us a form of haptic feedback into that. So, and then for the shape-shifting structure, the first part of the project I was talking about, that we're working more in the direction of using it for exploring new planets, like for space applications. So where, again, having batteries or having energy sources become very difficult. So using mechanical principle there can help a lot. And then there's a lot of research in the direction of mechanical computers. So we're used to have our computers based on electronics, on chips, but in many scenarios, it might be beneficial to think about mechanical components because we can build very, very small components where electronics would fail. So this can become then competitive with the electronics counterpart.
Very cool. Thank you. I think it's so cool to see how many real applications that your work can have. We got a question in the Q&A. It says, how much of your research uses physics versus math versus CAD versus something else?
Very good question. Yeah. So it's a good mixture. I like to get all the feedbacks from different areas and get idea from different fields. Even in my lab, we have students that are mechanical engineers, that come from physics, applied mathematicians, electrical engineers. So we combine all these expertise, really. We like to have more of an holistic vision in research and also interdisciplinary, because oftentimes, like, the frontiers between different research areas is where we can really make a leap there, and we can advance multiple fields at the same time. This is based on, experiments, computational, so type of work, and also analytical, like derivations. So especially because we want to demonstrate new properties that cannot be found in nature. So we need to be able to demonstrate them in the lab, but also to make sure that it just didn't happen by chance in the lab. So we need to justify where they're coming from. And that's when we use numerical simulations and math to design and help us understand why we see certain phenomena in the lab.
Thank you. So, kind of on to go a little deeper in that, a lot of our audience are high school teachers.
Mhm.
So, what foundational science and math concepts do you think high school students should focus on to prepare for fields like yours?
Great question. Yeah. So, my mom, she's an high school teacher, so I love, I love speaking to this audience. So, yeah, I think the foundational work really needs to come from, showing the connections between math, physics, also chemistry and biology, because I feel that it's not too much about just learning a concept, but it's being able to contextualize it and to bridge those different areas. So, and that's a lot of the work that then we do at engineering as well, where we take the math and we say, okay, cool, now how do we apply this to different scenarios, right? So math is always the same, right? So I always tell the students, like, that is your best friend, like, it's not your enemy, because it will never betray you. He will always be by your side, and it's going to be able to help you address a variety of problems, just because you go back to the foundation and to the basic. So I think, start building those connections across multiple fields and bridging that to what is a real world application, but also an abstraction on going far out, because we don't want the math just to be applied to one specific case, but to be able to apply it to a variety of cases. That's very important. I think it's something that we keep doing by saying, okay, like, zoom out and zoom in, like zoom in into the application, zoom out back to the math, and reiterate. Because if we just focus only on the application, we might be losing, like, missing something that is around us that might help us broadening the perspective. And if we are only on the theoretical aspect, then we might struggle to combine the two things. So I always invite students, like, to go out in nature, walk around, and see if they can, understand some of the principle of how leaves are moving, why they're moving that way, or currents, in the ocean. So there are so many, like, sources of inspiration. Like, I teach also vibrations, so dynamics of structures. So we get a lot of vibration examples just by looking at our, I don't know, washer, for instance, or anything. So just trying to trigger that curiosity and always bridge the gap between what we see in class and what is out there, and say, if you had to model your washer, how would you do it? Like, where would you start from? So maybe, stimulating that type of questions and connections, I think it is a great starting point.
Thank you. I love that. You kind of segued into my next question that I was wondering about. Are you aware of any classroom-friendly demonstrations or activities or even outreach programs that can illustrate either principles from your research or just in engineering in general that could be useful?
Sure. So we are developing some of those, also with some, gadgets, simple demonstrations that students can play with. Like, you have the jumping popper, like, that is based on instability, and that is a very fast motion. So like kids might have seen that, at their dentist every time, but, they might not have looked at it as something more than a toy, but it actually has very interesting ideas behind that, like beetles use it to jump from across different stairs. So yeah, we're trying to put together some of that material with demonstrations that could be reproduced in a lab, and some videos too, like showing how animals like tackle this type of challenges when they need to either catch a prey or jump very high, to show that there is the same mechanical principle behind that. So then if you had to model it with equations, they would be the same equations. So yeah, we're gonna be able to share more, but yeah, we're currently working on gathering this type of material and classify it across multiple disciplines in a way that can, spark interest in the student and inspire them.
Oh, perfect. Well, when you do have more to share, we would definitely be interested in helping to get that out and spread.
Awesome.
We got another question in the chat. It says, how long did something like the little Pac-Man gripper take to develop?
Oh, good question. So, okay, I always start as an idea, like research ideas oftentimes look like, either jokes or simple things. I say, oh, what if, right? So from that inception moment to the realization, maybe it took us 9 months for the whole pipeline. And then in the meantime, we were working on the simulations aspect. So I would say to have the first prototype that we could confidently say, okay, this works in a way that we can predict. It took us a year. And then running all the experiments, data collection, that takes, I would say, at least 6 months. And then, we can advance it with different variations. So the good aspect is to have, a good foundation. Then from there, you can spin it in many ways in parallel. But until you don't get initial validation between what you're seeing in the lab, what your code numerically is telling you, like with the deformation, and what your equations are telling you, until you don't have all these check boxes, like you cannot move forward too much. So I would say those are the main milestones that we tackled in a year or so.
Thank you. We have time for one more question. I don't see any others coming in. Thank you to everyone that put some of the resources into the chat.
One.
So just kind of to wrap up a little bit about you, what inspired you to pursue a career in mechanical engineering, and how might teachers spark this interest in their students?
Yeah. Yeah, I love these questions because I think I owe like everything I've done to my teachers. So I would always need a long list of acknowledgements to name all of them. So I think it's always been, a curiosity-driven approach that my teachers, instilled in me. So anything that was fascinating. Like I love sailing, for instance, and that there was a lot of physics going on in sailing, right? Because you had the fluid, you have the water underneath, you have the air, you need to pull strings here and there to get to the point where you're gonna get, right? So as a child growing up, like you say, okay, how does this thing work, right? How can I make it that is optimal for my purposes? And then I got intrigued also into aerospace applications. That's why my background is in aerospace as an undergrad and a master. I did aerospace engineering because again, it was the way an aircraft is flying is very similar to the way we were sailing, right? So you expand on that, and then I got interested into arterial mechanics or biomechanics tissue because again, how the blood flow flows through our arteries is very similar to the way an aircraft wing is being designed. Because I'm always tracking what are the equations, right? What is behind the scenes, and those are very similar principles and concepts. So yeah, I think my teachers always encouraged me to go in the direction where what I was curious about without putting boundaries. So that's how I ended up being in a mechanical engineering department with an aerospace engineering background, doing also biomedical engineering and developing soft intelligent materials. So blending and not putting constraints to the curiosity.
Thank you. We did get one more quick question. Can you recommend a few good books?
Oh, good point. I would need to think about it because I read there are lots of books that inspire me. It's about stories of women in science, so that they serve as a source of inspiration. Lots of them are Italian women in science. I'm Italian by origin. So there is the story of, okay, Rita Levi Montalcino. She won the Nobel Prize for medicine. Margarita Ack, she's an astrophysicist. And those are some of, the key figures, and their stories and their biography have always inspired me. But I also need to admit that my big passion as a scientist is on theater. So there is, the Book of Life of Galileo, that again, thinking about the curiosity about pushing the boundary of science, have always inspired me, and I highly recommend it for high school students, actually. So we did a play when I was a high school student, and I think that was an important turning point of my curiosity-driven passage.
Thank you. It's been so great hearing from you today and just learning about you and what you do. Thank you so much for taking the time to be here with us. If anyone does have any additional questions, you can email me and I'm happy to forward them to Dr. Tubaldi, and I will get back to you all. Next, I would like to extend a special thank you to our sponsors for supporting us and making these cost-free webinars possible for you all. And lastly, I want to thank all of you in the audience today for attending the webinar. We hope you enjoyed it. I kindly ask that you take a minute to fill out our post-webinar survey. Your feedback makes it possible for us to serve your needs. The links to the surveys will also be emailed to you so that you can complete it at your leisure. Thank you, thank you, thank you again to our speaker, Dr. Tubaldi, and to all of you all for joining us today. Yes, and be sure to be on the lookout for our future events. Thank you to everyone again so much.